This video is Chapter 13, Part 5, Energy and Circular Orbits. It corresponds to Section 7 in your textbook. So this is kind of like a continuation of what we did in the gravitational potential energy video. So we can easily derive the kinetic energy of an object in circular orbit by knowing that the centripetal force is caused by gravity. So this is the object in the center, some kind of star, and here's a planet orbiting the star. The star and the planet are a distance r from each other. Their centers are a distance r from each other. And the force of gravity is what's causing the planet to rotate. So the gravitational force is equal to the centripetal force. So gmm over r squared is equal to mv squared over r. The big M is the star in the middle, the little m is the planet. We can cancel out one of these m's, we can cancel out both these m's. We can cancel out one of these r's, and we get that v squared equals gm over r. If we solve that for v, we get that v is equal to the square root of gm over r. And this is actually one of Kepler's laws, which I'll probably be doing in the next video. Now the kinetic energy of this object is 1/2 mv squared. So we simply plug this in right here. And when you square a square root, the square root part goes away, and we end up with the kinetic energy of an object in circular orbit being equal to this expression right here. So that'll come in very handy in this video. Let's do an example problem. A playful astronaut releases a bowling ball of mass m equals 7.2 kilograms into circular orbit about Earth at an altitude h equals 350 kilometers. What is the total mechanical energy of the ball in its orbit? And in order to launch the ball from Cape Canaveral, what speed would it need to have been given? Discount the rotation of the Earth. So there will be another problem in this video where we do not discount the rotation, so just keep that in mind. When something is on Earth's surface, it has a little bit extra kinetic energy because it has a speed due to the rotation of the Earth. So the first thing we're going to do is calculate how far the center of the bowling ball is from the center of the Earth. So it's at an altitude of 350 kilometers, which is 350,000 meters, and we have to add that into the to the radius of the Earth, which is 6.37 times 10 to the 6 meters. You can find that on a table of information. So the bowling ball is 6.72 times 10 to the 6 meters from the center of the Earth. So we want to find the total mechanical energy. When the bowling ball is in circular orbit, it has gravitational potential energy and kinetic energy. So its gravitational potential energy will be equal to negative gmm over r. So we just plug in numbers, and we get negative 4.275 times 10 to the 8 joules. Now for kinetic energy, we want to use the formula we just derived. We want to plug in the correct numbers, and we get 2.13774 times 10 to the 8 joules. Now to get the total mechanical energy, we just add the kinetic and the potential energy, plug in numbers, and we get negative 2.13774 times 10 to the 8 joules. Now part B asks, in order to launch the ball from Cape Canaveral, what speed would it need to have been given? We need to use the concept of conservation of mechanical energy. So on the Earth's surface, the bowling ball will have gravitational potential energy. So that's what this means, Earth's surface. We want to plug in numbers. And we get that the gravitational potential energy of the bowling ball on Earth's surface is negative 4.5104 times 10 to the 8 joules. Now, since mechanical energy is conserved, the gravitational potential energy that the bowling ball has on Earth's surface plus whatever kinetic energy it's given will be equal to the total mechanical energy that it has while it's in orbit. So we can use this information to solve for the speed that we need to give the bowling ball. So we just want to go ahead and plug in numbers. So this is the gravitational potential energy on Earth's surface that we just calculated. This is the kinetic energy we want to give it. And this is the total mechanical energy of the object in orbit that we calculated on the previous slide. M will be equal to 7.2, that's the mass of the bowling ball. So we just solve this expression for V. And we get that V is equal to 8,118 meters per second. So we got to get that bowling ball to be going pretty fast in order to get it to orbit at a height of 350 kilometers above the Earth's surface. Let's do another example problem. So we have a hypothetical planet called Zero. It has a mass of 5 times 10 to the 23rd. Oh, and that should be kilograms. And then the radius, that should be meters. Sorry, I forgot to write that in. Meters and kilograms. And it has the same rate as rotation as Earth. So we have a 10 kilogram space probe that is to be launched vertically from its surface. The inhabitants of this planet want this probe to orbit this planet at an altitude of 4 times 10 to the 6 meters. For the following questions, we want to ignore air resistance but include the effect of the planet's daily rotation. So what is the minimum energy input necessary to place the probe in orbit, and what speed would this correspond to? So again, we want to use conservation of mechanical energy. Whatever mechanical energy the probe has on Zero's surface, it should have that amount of mechanical energy when it's in orbit at that 4 times 10 to the 6 meter altitude. So the energy that it has in orbit will be equal to its kinetic energy in orbit plus its gravitational potential energy in orbit, which will be equal to that expression there. So the kinetic energy minus the potential energy, because the potential energy has a negative sign in there. And actually, this is kind of important. The mechanical energy of any object in circular orbit will be equal to this expression right here. So I wouldn't necessarily memorize that, but you should be able to derive it. So, the energy of this probe in orbit will be equal to G times the mass of the planet times the mass of the probe divided by 2r. And r needs to be the radius of planet Zero plus the altitude that you wanted. So this will be the mechanical energy of the probe in orbit, this number right here. And since mechanical energy is conserved, we need to make sure we find both the potential and the kinetic energy of the probe when it's on Earth, when it's on Zero's surface. So because this planet is rotating, the probe will have some kinetic energy due to Zero's rotation. And it will have a speed of distance divided by time, just our 9th grade formula for speed. And that'll essentially just be equal to the circumference of the planet divided by the time for one rotation. The time for one rotation is 1 day, or 24 hours. So this right here is the circumference, that's 1 day. And then this is the radius of the planet, and this is 1 day converted into seconds. So the speed of the rotation of that planet is equal to this number right here. Now, we know that the mechanical energy is conserved, so the initial mechanical energy will be equal to the final mechanical energy. So this is the initial gravitational potential energy of the probe on the planet's surface. This is the kinetic energy due to the rotation of the planet. You see that 218.17. And then this is the energy that needs to be inputted. And then this is this is the total mechanical energy of the probe when it is in orbit. So we can just go ahead and solve that for E input. We get that the input energy, so the energy we need to give to the probe somehow in order to get it to orbit, is 8.715 times 10 to the 7 joules. Now part B asks us what speed would that correspond to. Well, we can just set this number equal to 1/2 mv squared. We know that the mass of the probe is 10. And when we solve for V, we get that V is equal to 4,174.9 meters per second.